Hello everyone. Today we're going to learn about breadth first search algorithm. We have learned about breadth first search in tree and graph data structure. But in today's dedicated tutorial, we're going to officially learn about breadth first search. What it is, what kind of problem does it solve, and how to use it effectively. Prerequisite. We're going to use a lot of graph data structure in this tutorial. So make sure that you're comfortable with graph data structure before you continue. This tutorial is a part of the data structures and algorithms class. First, we're gonna learn what is breadth first search algorithm. But before that, we're gonna do a quick review on graph. A graph holds a relationship between the nodes. For example, relationship between airports. This is a visual presentation of the relationships between the airports. And right down below, we have the code presentation of this relationship. And we're using adjacency list. This is our graph. It holds the relationship between the nodes. In our example, the nodes are the airports. A node holds data that describes something in real life. In our example, our node is airport. For example, San Francisco Airport, New York Airport, Chicago Airport, and so on. So the graph presents some real-life relationship into code. Now, a purpose of a graph algorithm, like breadth first search that we have here, is to visit the nodes in a particular pattern, useful pattern. Our graph algorithm today is breadth first search. Breadth first search means that we're gonna search as broad as we can first until we move on to the next level. Let's have a look at our example here. This is the graph of our airport. And if we start at node Denver, node number 2, with breadth first search, we're gonna visit all neighbors of Denver node before we move on to the next level. Denver neighbors is layer 1. Next, if we start searching from San Francisco node, the neighbors of San Francisco gonna make up to layer 1. They are ORD and DEN. So with breadth first search, we're gonna visit ORD and DEN, which is layer 1. And when we finish with all the nodes in layer 1, we're gonna continue with layer 2, which has JFK and IAH. So that is the order of node visitation of breadth first search. It's layer by layer, the closest layer first. Now always remember to use queue data structure to achieve this pattern of node visitation. So for breadth first search, we're gonna queue up the starting node, we dequeue the starting node, then we enqueue all the neighbors of the starting node, which is SFO, ORD, JFK, and IAH, all neighbor nodes of starting node, the layer 1 nodes. And then we're gonna keep dequeuing and process the node. If we start from SFO, we're gonna do the same thing. We're gonna enqueue SFO, then we're gonna dequeue SFO, and enqueue the neighbors of SFO, which are ORD and DEN, the layer 1 nodes. Then we're gonna dequeue these nodes and enqueue their neighbors, the layer 2 nodes. And that's how we use queue to create this level by level node visitation pattern. Now, not only that we can use BFS for graph, we can also use breadth first search for matrix. For example, here we have a matrix that's representing a maze, and a cell with the number 1s in there are the walls that we cannot travel to. If we think about it, this matrix is one kind of the graph, which is a cell is a node. So if we start here, this first node is connected to the node on the right because we can travel to it, whereas it's not connected to the node below, the cell with the number 1 in it here, because we cannot travel into it. So you can see we actually can have a one-to-one mapping of this matrix to a graph. We will talk about it more in detail later. But for now, we know that we can use breadth first search to search for a possible path in this maze to find a way to go from here to our final destination here. And we're gonna learn how to do it later. Next, we're gonna have a look at breadth first search simplest code implementation. As we use breadth first search in different purposes, the code can get complicated really quickly, so it's good to remember the simplest code implementation of breadth first search. And that's what we're gonna do for this part. Again, breadth first search is a graph algorithm. The pattern of node visitation is level by level. We can think of it like layers of onion rings, like this example that we have here. We have the first layer of ORD and DEN, and the second layer of JFK and IH. Or if our starting node is DEN, then the first layer gonna be SFO, ORD, JFK, and IAH. Again, BFS visit all neighbor nodes before moving on to the next set of nodes, meaning the next level. For layer 1, we only need 1 move to reach all the nodes. Layer 2, we need 2 moves. Level 3, 3 moves, and so on. What that means is, if we start at SFO, for our layer 1 node here, we only need 1 move from SFO. The blue line here is is the move. So we only need one move to go from SFO to ORD or SFO to DEN. For layer 2, we need two moves to go from SFO to ORD and to JFK. That's two moves. Or to go from SFO to DEN to IAH. That's two moves. So layer 1, one move. Layer 2, two moves from the starting node. It's the same thing that we have here. If we start at DEN, we only need one move to reach all of the neighbors. So from DEN to either FSO, ORD, JFK, or IAH, we only need one move. Now because of this nature, one of the usefulness of breadth first search is to find a sorted path from one node to another, only if we have equal edges, meaning all of the edges had the same weight or unweighted, like this example we have here. So this graph have unweighted edges, and if we want to find a sorted path, we absolutely can use breadth first search. In general, the usefulness of breadth first search is to solve a problem that visiting node layer by layer is useful. That means if we have a problem, we're gonna apply the node visitation at layer by layer, and we see if it solves the problem. And if it does, then breadth first search is useful. And remember always to use Q to implement breadth first search algorithm. Next, we're gonna have a look at the simplest implementation of breadth first search. In this implementation, for our example here, we're just gonna visit all the nodes and print them out layer by layer. So it's gonna be SFO, the starting node, layer 1 of ORD and DEN, and then layer 2 of JFK and IAH. First, we have the graph that represents the relationship between the airports. Then we have the map of the node indexes and airport names. In addition to airport names, in real life, we can actually have any information we want here in this object of a node. Next is our implementation of breadth first search. Our breadth first search is gonna take in the initial node index. We initialize an empty result array. We initialize a set that's gonna have all the nodes that we have visited, and we initialize our queue with the starting node. Now always remember to use a proper queue data structure in real life. Here for quick implementation, I'm using an array, and that's not efficient. Always remember to use a proper queue data structure. Here we print out our starting airport, and this is our breadth first search while loop. It's very simple. While we still have data in the queue, we dequeue the node in the front. In this case, that's gonna be SFO. If we have never seen this node before, we process it. Otherwise, we're gonna ignore it. So if we never seen this node before, now we've seen it and remember we have seen it. Then we get all the node neighbors. And for each of the neighbor, if we have never seen the neighbor, we're gonna enqueue it. After that, we simply save the airport that we're processing in the result array. Here we print out the result. And if we run our breadth first search, starting from node 0, which is SFO here, this is our final result. We have SFO for the starting node, ORD and DEN for the first layer, JFK and IAH for the second layer, like what we have here. We can also play around with our algorithm. For example, if we change the starting node to DEN with the index of 2, like so, then our result is gonna be DEN, the starting node, and SFO, ORD, JFK, and IAH for the first layer. And that's exactly that we have here. Breadth first search in simplest form. It's quite simple. It's easy to understand and easy to implement. So make sure that you master this step first. Because with different requirements, for example collecting the nodes along the path, the implementation is gonna get complicated very quickly. So just make sure to get comfortable with this first block of implementation of breadth first search before adding more complicated logic. Now that we have known how to do breadth first search, next we're gonna see the typical problems solved by the breadth first search algorithm. And there's a lot of problems that we can solve with breadth first search. But first, when you're given a graph problem, always remember to identify the nodes, construct the graph, then apply breadth first search node discovery pattern, which means level by level, to see if it solves your problem. Our typical problem that can be solved by breadth first search are sorted path. Sorted path from point A to point B, we can only use breadth first search if the edges weight are equal. Otherwise, if it's not equal, we have to use depth first search, which we're gonna learn after this tutorial. So, sorted path with equal edge weight, breadth first search. Sorted path with not equal edges weight, depth first search. Another typical problem is path finding, which we're gonna answer is there a possible path between two nodes, or finding common friends in social network, or finding the best route for network package, or having a good web crawler strategy, or more graph intensive application like cycle detection, or to see if a graph is bipartite. They all can be solved with the node discovery pattern of breadth first search, level by level.